Okay, let's think for a sec about water. In many places, getting clean drinking water isn't just a simple turn of the tap, especially in really dry parts of the world, arid or semi-arid regions. Finding good groundwater there is just
Yeah,
crucial.
it absolutely is. And that specific challenge, finding high-quality drinking water from groundwater sources, is what we're digging into today.
Right. And you, our listener, actually sent over some fascinating material on exactly this, assessing groundwater quality. So we're doing a bit of a tailored exploration based on that, focusing on this article, Decision Tree-Based Data Mining and Rule Induction for Identifying High-Quality Groundwater Zones to Water Supply Management. Quite a title.
Yeah, it is. But our mission here is basically to unpack how they use these, well, really smart data mining techniques, specifically something called decision trees. The goal was to see if these could help, pinpoint those really valuable spots of high-quality groundwater.
And there's a twist, right?
Yeah,
Something about how they looked at the data.
exactly. There was a kind of surprising finding about the best way to analyze the water quality info, which we'll definitely get into. It shows how focusing on specific water characteristics can lead somewhere unexpected.
Okay, cool. So the study itself, it's centered on Tabriz City in Iran, a place where water is obviously a very big deal.
Hmm.
And what I like is that it's not just theory. They used real world data, right? From what, 80 wells?
That's right, 80 observation wells. So it's grounded in actual measurements. And they combine these data mining algorithms with GIS, Geographic Information System.
Ah, the mapping side of things.
Yeah, to see which combination, which algorithm really nailed identifying those high-quality zones.
So let's start with the basics. Why is it so hard to find this high quality groundwater?
Well, I mean, we have standards, right? Like the WHO globally or ICER in Iran setting minimums for drinking water. But just scraping by, just meeting those minimums, that doesn't always mean the water is genuinely, good for drinking long term. It might be just borderline acceptable.
Right. It's not just about one or two things being below a limit. It's more complex.
Really is. It's about how a whole bunch of factors interact.
Mm.
And that's where the researchers brought in this idea of a DSS, a decision support system.
Okay.
Because when you've got all these different measurements, maybe on different scales, you need a systematic way to make sense of it all.
And GIS helps visualize that spatially, I guess, where the good and bad spots are.
Precisely. GIS gives you the where. But this study went further. They didn't just map existing quality levels. They used data mining to try and predict or classify the quality based on the underlying data.
Okay, so data mining, like digging for patterns in the number.
Exactly.
Yeah.
Sifting through all that well data to find hidden rules or relationships that we might miss just looking at it. And they focus specifically on these decision tree algorithms. You can
Right.
sort of picture them like flowcharts, asking a series of questions based on the data, like if the chloride level is this and the pH is that,
Yeah.
to eventually classify a zone, high quality or not.
And they tried out a few different types of these decision trees.
They did. 5 main ones were compared. There was the ordinary decision tree, or ODT, then random forest, RF, random tree, RT, also Chi-H-Aid, which stands for Chi-Square Automatic Interaction Detector, and finally ID3, Iterative Dichotomizer 3.
Okay, quite the lineup. Different tools for the job, essentially?
Yeah, different ways of building that classification structure, that sort of prediction map based on the input data.
So what was the input data? What exactly were they measuring in those 80 wells?
They started with 8 initial variables, things like sulfate, hardness, total anions, pH,
Okay.
calcium, magnesium, chloride, and EC, which is electrical conductivity. Basically, how well the water carries a current, often related to dissolved salts.
8 parameters. But then you mentioned they narrowed it down.
Yes, and this is a really neat part. They used a technique called feature selection. And interestingly, one of the algorithms itself, Random Forest, actually helped them identify which of those 8 were the most influential, the best predictors.
Ah, so the algorithm itself helped find the most important clues, like a detective focusing the investigation.
Kind of, yeah. And it turned out that 4 key parameters really rose to the top:
Which ones?
hardness, pH, chloride, and EC.
Just those 4 out of the original 8.
Primarily, yes.
Hmm.
The analysis showed these 4 gave the strongest indication of overall water quality for their classification purposes.
That's really important. It means you potentially don't need to measure everything all the time. Focusing on these key indicators could be much more efficient.
Exactly. Efficiency and effectiveness. Get the most bang for your buck, analytically speaking.
Okay, so they have their key parameters. Now, you mentioned something earlier about a surprise related to how they analyze the data.
Yes, this is crucial. They looked at the data in 2 different ways. First, as continuous data, basically, the exact numerical measurements they took, like pH 7.2, EC 650, hardness 210, and so on.
The raw numbers.
The raw numbers. But they also tested analyzing it as discrete or categorized data, meaning they grouped the values into classes based on existing standards.
Yeah.
So instead of EC 650, they might just classify it as good or permissible or unsuitable based on predefined thresholds.
Ah, I see, like putting them into buckets.
Exactly. They use specific thresholds from other studies to define these buckets for EC, chloride, hardness, and pH. So very defined categories.
And they ran their 5 decision tree algorithms on both types of data, the raw numbers and the categories.
They did. They wanted to see which approach worked better for prediction.
And this is where the surprise came in.
This is the big one. The results were dramatically different. The algorithms performed much, much better when using the continuous numerical data, the raw numbers.
Really? How much better?
Significantly better. For the continuous data, random forests, RF, came out on top with a really impressive accuracy, 97.10%.
Wow, 97%. That's high.
Extremely high for this kind of environmental modeling. The ordinary decision tree, ODT, also performed very well, and the random tree, RT, was acceptable too. They used several statistical measures to confirm this, not just raw accuracy, things like the Kappa coefficient, Spearman-Rho, Kendall-Tauk. It was a robust evaluation.
Okay, so RF, ODT, RT works great with the raw numbers. What happened when they used the categorized data, the buckets?
Well, the study flat out states the accuracies were very poor in comparison.
Ouch!
Yeah. I mean, one algorithm, ID3, performed best for that type of categorized data, but its overall accuracy still wasn't anywhere near what RF achieved with the continuous data.
So the clear takeaway is, don't categorize your data beforehand if you want the best prediction. Use the actual numbers.
For this type of problem, using these decision tree methods, yes. The numerical methods, ODT, RT, and especially RF, were just much more suitable. It suggests those finer details in the raw measurements contain really important information that gets lost when you lump things into broad categories.
That makes sense. Sometimes nuance matters. Okay, so they found the best algorithms, RF, ODT, RT, and the best data type, continuous. What did they do with that knowledge?
They took the rules generated by these top-performing algorithms, those if-then scenarios based on the continuous data, and used them within their GIS.
To make maps.
Exactly, to create groundwater quality maps for the whole study area,
Yeah.
predicting the quality even in places where they didn't have a well.
How did they do the prediction for the map itself? Interpolation.
Yes, they used a geostatistical technique called ordinary kriging, to estimate the spatial distribution of those key parameters, hardness, pH, chloride, and EC.
Right, a standard way to fill in the gaps on a map based on nearby measurements.
Correct. And they were careful, too. They checked if nearby values were actually related using something called Moran's I-index spatial autocorrelation.
Good.
And for some data like EC and hardness that wasn't normally distributed, they applied a transformation, a log normal one, to make the kriging work better. Pretty thorough stuff.
Sounds like it. So what did these final maps show? Did they reveal anything interesting about the Tabriz area?
They did. A general trend emerged pretty clearly. The groundwater quality tended to decrease, get worse, as you moved from south to north, and also from east to west across the study area.
Okay, a geographic pattern.
Yes. And importantly, all the maps generated using the rules from ODT, RT, and RF consistently identified the southern parts of the area as having the optimal quality for drinking water.
So all the top methods agreed on the best general location.
They did, which gives you more confidence in the result.
Were the maps identical?
Not exactly identical. The study mentions slight differences, which makes sense because each algorithm generates slightly different predictive rules.
Right.
But given that random forest had the best statistical performance overall,
its map is probably the most reliable one to go by.
that's the conclusion, yes. The RF-based map is considered the most dependable guide to finding those high-quality zones.
And that 97% accuracy, that really means something in practice, doesn't it? If you're deciding where to drill, that level of confidence is huge.
Absolutely huge. Think about the cost and effort of drilling wells. You want the best possible information before you start.
This really brings it back to the real-world value, especially in places like Tabriz, facing water stress, maybe droughts.
Exactly. Knowing precisely where the best potential sources are is critical for water supply management. This combination of data mining and GIS gives resource managers a really powerful targeted tool.
And I also like that point about data mining translating expert knowledge into usable rules.
Yes, it takes complex relationships that maybe only a hydrogeologist understands deeply and boils them down into these more straightforward, if hardness is X, A, and D, pH is Y, then quality is Z type rules.
Which means potentially non-experts could use the output of the system to make informed decisions, right?
That's the potential, yes. It makes complex analysis more accessible for practical decision-making on the ground.
Okay, so wrapping this up then, the big insight, the main takeaway from this deep dive.
I'd say it's the clear demonstration that decision tree data mining, especially using continuous numerical data and an algorithm like random forest, is a highly effective, very accurate method for identifying high-quality groundwater zones.
Don't pre-categorize your data if you want the best results from these methods. Use the numbers.
That seems to be a key lesson here, yes.
And presumably, this approach isn't just limited to Tabriz.
Oh, absolutely not. The potential application in other water-scarce regions globally is pretty obvious. The methodology itself, combining robust data mining with GIS for spatial analysis, could be valuable for all sorts of environmental assessments, way beyond just groundwater.
Yeah, you could see it being used for soil quality, maybe air pollution mapping. Lots of possibilities.
Definitely.
So maybe the final thought for you, the listener, to chew on. We see these powerful analytical techniques emerging. Given the mounting pressure on global water resources, both quantity and quality, how can we take tools like these, refine them, and crucially get them implemented more widely?
Right. How do we scale this up to help ensure more communities, everywhere, have sustainable access to the clean drinking water they need? It really highlights the potential and maybe the responsibility of using technology smartly to tackle these huge environmental challenges.